Hello, mathematicians. Let's continue our discussion of the logic of quantified statements. In particular, we want to look at what happens when you have multiple quantifiers in a statement. And forewarning, it gets confusing, y'all. Sometimes you really have to pause and think through multiple times what is being stated here. So, when we find more than one quantifier in a statement, we imagine the actions suggested by the quantifiers as being performed in the order in which the quantifiers occur. So, for example, let's say we have this statement, and you'll notice we have a universal quantifier and we also have an existential quantifier. It says for every x in set D, there exists a y in set E such that x and y satisfy the property P of x comma y. To show that a statement like this is true, you must be able to meet the following challenge. Imagine that someone is allowed to choose any element whatsoever from the set D, and imagine that person gives you that element, call it X. So we're talking about this part right here. It says for every X in set D. So we should be able to accept any X value from the set D and do the following. Our challenge is to take that X value and find some element Y in set E so that taking that X you've been given and the Y you selected, and together they satisfy some property P. Now, because you do not have to specify the Y value until after the other person has specified the X, you are allowed to find a different value of Y for each different X you are given, if necessary. We're going to skip the Tarski example for now, but if you want to walk through this, this PowerPoint will be in Canvas under the module for PowerPoints. I'm going to skip to this summary. We've already talked about this combination. For every x in D, there exists a y in E such that P of x. Again, your challenge is to allow someone else to pick whatever element x in D they wish. Then you must find a particular element in Y that works with that particular X. What if the quantifiers are reversed? What if it says there exists an X in D such that for every Y in E, P of X comma Y? This time, your job is to anticipate any value of Y someone might give you later. So you're going to select a particular X value in D that will work no matter what Y value in E anyone might choose to challenge you with. Let's practice with this example. We have a college cafeteria line with 4 stations. We have salads, we have main courses, we have desserts, we have beverages. We have 3 students, Uta, Tim, and Win, and they've selected a variety of items from the stations. And we have a little tree diagram showing what each student selected, which we'll refer back to later. Write each of the following statements informally and find its truth value. First one is example A. It says there exists an item I such that for every student S chose I. So I'm going to try to think of an item such that no matter which student you give me, Uta, Tim, or Win, I can say that that student selected that item. So I'm going to look for an item that every student selected. Is there such an item? When I look at this diagram, I'm looking for an item that has 3 lines going to it. Do you see it? There is such an item. So I have selected a particular item such that no matter which student you give me, I can say that student selected that item. So this is true. Part B says there exists a student S such that for every item I, S chose I. Okay. So now I'm going to look for a student such that no matter what item you pick, I can say that student picked that. Really, what I'm looking for is there a student that selected every item? Well, Tim tried. He came pretty close. He selected quite a few things, but he did not select every item. So, no, that's not going to be possible. Okay. So, I can't find a student that selected every item. So, this one is going to be false. Once again, I encourage you, pause this video, digest this statement one part at a time. I certainly had to. I had to think about these. And I still might make a mistake, but let's move forward and see if I can get through it. In part C, it says there exists a student S such that for every station Z, there's an item I in Z such that student S chose I. Okay? Ooh, let's see. Let's move forward and see if we can get some help on this one. This says there is a student who chose at least one item from every station. Now, this is true. Both Uta and Tim chose at least one item from every station. Again, reread that. There exists a student S such that for every station Z, there is an item I in Z such that S chose I. Now, if you got lost about halfway through that sentence, guess what? So did I. But I encourage you, pause, read that. Go back and look at the diagram. Read the informal statement. Process that, because that's a tough one. So is this last one. For every student S and for every station Z, there exists an item I in Z such that S chose I. So someone should be able to give me a random student and a random station, and I should be able to pick an item I in that station that this particular student chose. Every student chose at least one item from every station. This is false because Wynn did not choose a salad. Again, read that again. That it's so easy to get lost in that statement. Read the informal statement that goes with it. See if you can make some understanding of that given this diagram. So those last two are quite challenging. But certainly these first two statements you should be able to follow with ease. Well, relatively speaking. So, as we've been doing all along, it's very important that you are able to translate from informal language to formal mathematical language and vice versa. So let's practice. We have a statement, it's telling us that the reciprocal of a real number A is a real number B such that A times B is equal to 1. The following two statements are true. Rewrite them formally using quantifiers and variables. Every non-zero real number has a reciprocal. Look at the translation. For every non-zero real number U, there exists a real number V such that U times V is equal to 1. Look at the second example. There is a real number with no reciprocal. There exists a real number C such that For every real number d, c times d is not equal to 1. Again, I really encourage you, pause this video, read these again. Look at these translations. Process it. That's really the best thing to do. Just pause and think through what each of these is saying. We have another example, uh, complicated. I mean, this is a calculus example. The definition of a limit that we study in calculus uses both quantifiers, for all and there exists, and also if then. We say that the limit of a sequence a sub n as n goes to infinity equals L, written thusly, if and only if the values of a sub n become arbitrarily close to L as n gets larger and larger without bound. More precisely, this means that given any positive number epsilon, we can find an integer n such that whenever n is larger than capital N, the number a sub n sits between L minus epsilon and L plus epsilon on the number line. Symbolically, it says for every epsilon greater than 0, there exists an integer capital N such that for all integers little n, if little n is greater than big N, then L minus epsilon is less than a sub n is less than L plus epsilon. What? Considering the logical complexity of this definition, it is no wonder that many students find it hard to understand. Ambiguous language. So, this is a famous example of visual ambiguity. So, you've probably seen this before. I've seen it since I was a child. So, depending on how you look at it, you either see the silhouette of a young woman wearing a large hat turned away or an elderly woman with a large nose. So, we have to be careful with ambiguity in mathematics, is the point. Again, negating statements with more than one quantifier can be really tough. But we can use the same rules to negate statements with several quantifiers that we would use to negate simpler ones. So we've already talked about these first two. To negate a for every x in d p of x, we simply need to say there exists some d such that p of x is not true. And to negate a there exists, we say, well, for all, not p of x. So let's look at how we would negate for every x in d, there exists a y in e such that. Look at how the negation goes. There exists an x in d such that for every y in e, not p of x. So look at these two. This is kind of the middle guy. How did we get there? Okay. So the negation of for every there exists is there exists such that for every. And here is a summary of those negations. So again, think through these. To negate a for every there exists such that p, we say there exists such that not p. And the opposite is true. Again, take a moment, think through that. Again, we're going to skip the Tarski example. All right, order of quantifiers. Consider the following two statements. For every person X, there exists a person Y such that X loves you. And there exists a person Y such that for every person X, X loves Y. Think through that for a minute. Note that except for the order of the quantifiers, these statements are identical. However, the first means that given any person, it is possible to find someone whom that person loves. Whereas the second means that there is one amazing individual who is loved by all people. I like this example. Pause and contemplate this one for a moment. Reread the statements carefully to verify these interpretations. The two sentences illustrate an extremely important property about statements with two different quantifiers. In a statement containing both the universal and existential quantifiers, changing the order of the quantifiers can significantly change the meaning of the statement. Interestingly, however, if one quantifier immediately follows another quantifier of the same type, then the order of the quantifiers does not affect the meaning. Here's some examples. Consider the commutative property of addition of real numbers. For example, for every real number x and every real number y, x plus y equals y plus x. So changing the order of these two statements, since they are both universal quantifiers, doesn't matter. So we could say for every real number y and every real number x, same thing. Since those are the same, we can write this a little more compactly, a little more economically by just saying for all real numbers x and y, x plus y equals y plus x.